So good evening everybody. Dark matter. Why is it dark and does it matter? So for quite a long time now, best part of a century, we've known that the universe has a dark side. And even a century later, it's still a bit of a mystery. So here you can see the lecture is, after the discovery of antimatter and dark matter, we've confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever. Okay, this is a talk not about doesn't matter, it's a talk about dark matter, and by the end of this talk I hope to have convinced you that the existence of dark matter does indeed have a distinct influence on the universe. So the embarrassing fact is that if we look at all the matter in the universe and separate it into two piles, all the matter we know about, all the stuff we know about, and the stuff that apparently is there but we don't really have a clue what's going on, then it's rather embarrassing to admit that the stuff we know about is only some 16% or so of the total matter budget of the universe. More than 80% of the matter that's out there is stuff that we really still don't have a good handle on. What about the 16%? What is the stuff we do know about? Well, we might think that the ordinary matter that's out there is, well, surely it's all of the galaxies and the stars that we can see. So presumably, given that all of the galaxies are made up of stars, surely that 16% is stars. Well, actually, no. Stars are actually only a small percentage of that. So of that 16%, 2% or thereabouts are stars, 13% is just gas. In fact, hydrogen and helium make up that 13%, although stars are doing their best to convert hydrogen into the heavier elements. They haven't done much of that so far. So in fact, the hydrogen and helium that was made in the Big Bang still makes up a large fraction of everything that we see in terms of normal matter. 2% is stars, and that final little 1% is a particular type of particle which we call a neutrino. It's not the sort of particle that makes up you and me. We're made up of neutrons and protons and electrons. A neutrino is a rather more elusive ghost-like particle, which I'll say a little more about later in the talk. So this talk is going to be covering what dark matter is in the sense of why do we call it dark matter, why is it dark? I'll be having a think about matter and light. And then we'll be looking at the evidence, and there's quite a few strands of evidence, and I'll be covering perhaps 3 out of the 4 that are written down there. We'll be looking at galaxies in clusters, stars in galaxies, and gravitational lensing. And I think I'll probably skip the cosmic microwave background, but it will be in the handout of the talk, which I'll provide you with later. Then we'll think about what actually makes up dark matter. What is it? And there are 2 candidates for what dark matter might be, and they go by the whimsical names of machos and wimps. And then I'll finish with, who cares? Does it actually matter whether or not we've missed a lot of the matter in the universe? And I'll show you that yes, indeed, it has a distinct influence on our universe. So firstly, why is it dark? Well, it's dark because it's not light. Well, that's a very facetious answer. Let's drill down a little bit more and think about what it actually means. Dark matter is some substance or another that does not behave the same way as what we're going to call ordinary matter or normal matter, the sort of matter we're used to. Because the sort of matter that we're used to thinking about interacts because matter is made up of charged particles. Some are positively charged, some are negatively charged. All the electrons in your body are negatively charged. All of the protons in your body are positively charged, and they interact through what we call the electromagnetic force because of all these charges that exist on these particles. And as a consequence, all of these charged particles interact through the electromagnetic force, and they emit and absorb, or they can emit and they can absorb, what we call electromagnetic radiation, what you would normally simply call light. And here light means not just visible light, it means any light, ultraviolet, infrared light, visible light, but the whole electromagnetic spectrum, all the way from X-rays to gamma rays up to radio waves. And hence ordinary matter can be detected because either it shines like stars, or glows like some gas if it's excited, or it maybe blocks the light from behind it and appears to be dark. And so it can be detected because it emits or absorbs electromagnetic radiation. But dark matter does none of these things. So in a sense, dark matter is not a very good name, because you would think that something that blocks light from beyond it and appears dark, maybe that's a candidate for dark matter? Well, no, dark matter does not absorb light, so a better name would perhaps be invisible matter or transparent matter, but unfortunately we're stuck with the name now. So everything that we are made of, pretty much everything we see in the world around us, is made of atoms. And atoms may emit or may absorb light. And we can think of an atom as being a little system like this, not quite a solar system, but it's got a positively charged nucleus and a whole load of negatively charged electrons buzzing around them like bees in a beehive or something like that. And it's because of these negative charges buzzing around a positive charge, and it's the changing behaviour of these electrons that can give rise to absorbing light or emitting light. We don't have to worry about the mechanism. All we have to care about is the fact that ordinary matter is made of things like this, and hence can emit and absorb light. So let's have a think at what the evidence is that there's something else out there that is not made of atoms and doesn't emit or absorb light. Let's have a think first about galaxies in galaxy clusters. What is it that holds galaxies together in a cluster? If we look at a big cluster, okay, there's one bright star at the top, but most of the other objects you can see here are galaxies that in a galaxy cluster. There might be perhaps 100 or a few hundred galaxies. The fuzzy objects, we've got a few foreground stars in there, but most of these fuzzy objects are galaxies. What is it that's keeping these galaxies together as a cluster? Why haven't they drifted apart? Are we just lucky to see in a particular part of sky galaxies that happen by chance to be in the same region of space? Well, that would be too much of a coincidence. Something is holding all of these galaxies together. And what is it? Well, it's not supposed to be a trick question. Gravity is holding all of these galaxies together. Gravity, of course, depends on the mass. So in order to figure out what is holding this galaxy cluster together, we need to get an idea of just how much mass is present. And it's rather tricky to do that directly, but we can, via a number of steps, get a pretty good estimate of how much mass is there. We can estimate it from the luminosity, because galaxies are made of stars, and as long as we understand what stars are, and how they're born and how they live and how they shine and how they die, then we should be able to get a pretty good idea of what a galaxy is made of. So if we measure the brightness of a galaxy, literally just see how much light it's emitting, then providing we understand stellar evolution and stellar processes, then we can have a pretty good guess as to how many stars there must be to make a galaxy that bright. If it's a really bright galaxy, presumably it contains more stars than a really faint galaxy. That seems a perfectly reasonable assumption. And not only can we estimate how many stars there are, given that we know, roughly speaking, how many faint stars there are, how many bright stars there are, we can figure that out by looking within our Milky Way to get an idea of how that works. We can also get an idea of how many stars are fairly low mass and how many stars are very high mass. So if we know how many trillion stars there are in a galaxy, we can estimate, by looking at the average mass of a star, we can estimate the total mass of all the stars in that galaxy. And hence we can get an estimate for the mass of the galaxy. You can see on the right hand side there I've said roughly. We can't get this down to 3 decimal places. We can't get it precisely. And we might estimate the mass of a galaxy, and we might overestimate or underestimate the mass by looking at how much is shining, and we might get it wrong by 10%, 20% or something like that. it's unlikely we're going to get it wrong by a factor of 2 or a factor of 3. So we have a reasonable estimate for the mass of a galaxy simply by looking at how much light is emitted by a galaxy. And for a cluster, we can do that for all of the galaxies that we can see. For 100 or 200 galaxies, we can do it for all of them, and then we have an estimate for the mass of that galaxy cluster. And so we can figure out how strong is the gravity that's keeping that cluster together. But there's a problem. Since almost 100 years ago, since the 1930s, it was realised that if you calculate how much gravity must be present based on the mass that you get from the luminosity of the galaxies, there is not enough mass to keep that cluster together. The galaxies should have drifted apart billions of years ago. We shouldn't see clusters like that if the only thing keeping them together is the mass that we can deduce from looking at how bright the galaxies are. Something is wrong. Originally it was called the missing mass problem because it was realised that somehow we're not accounting for all the mass that appears to be present. Using the luminosity to find the mass seems to underestimate the mass by a large factor, not 10% or 20% or 30%, but a factor of 2 or a factor of 3 or a factor of 5 or a factor of 10. There seems to be perhaps up to 10 times as much mass as we can see from just what is shining. Here's an expression I'm going to use more than once in this talk. It would appear it's as if there is some additional mass that is not luminous, that's not accounted for by looking at the brightness of galaxies. This extra mass is providing the extra gravity that's needed to keep the cluster intact and binds the galaxies together. What do we call this mass that is not luminous? Let's call it dark matter. That sounds pretty cool. As I've said, it's not strictly speaking dark. It's better to call it invisible matter, but we're stuck with the name. Okay, let's have a think about a second strand of evidence that tells us there's something going on out there that we haven't taken into account. Let's look at stars within galaxies rather than galaxies within clusters. All galaxies rotate to some extent, especially spiral galaxies that rotate in a very orderly fashion. How fast are the stars moving within the galaxy? Well, we can estimate that quite accurately by using the Doppler effect. Perhaps you're familiar with this. If we look at the spectrum of a source like a star, we tend to get dark absorption bands that are coming from particular elements that occur at particular wavelengths or particular colours, if you prefer. And if the star is moving away from us, those dark bands appear to be shifted towards the red end of the spectrum, and if the star is moving towards us, they get shifted towards the blue end of the spectrum. And so if we have a notional galaxy here that is spinning, and it's spinning in the direction indicated by the red arrows, then the stars on the left-hand side, indicated by A, are coming towards us, and so the spectrum should be blue shifted. Don't take that spectrum too literally in terms of the blue line next to the letter A. This is just schematic. And similarly, stars on the other side of the galaxy, labelled C, those stars will be moving away from us, and therefore they will be redshifted. Any star at the location indicated by B might be moving to the right or to the left or not moving at all, but those would not show a Doppler shift because we get the Doppler shift when we have velocities towards us or away from us. So if we look at the spectra of stars in a galaxy, we can get an idea of how fast they're moving. We wouldn't use a galaxy like this. This perhaps you recognise is the Whirlpool galaxy M51. We're looking at it essentially face on, and it's rotating in the sense that we can tell from the spiral arms, but you can see that the stars are moving as it were in a plane that's perpendicular to our line of sight. So essentially none of the stars are moving rapidly towards us or away from us. So that would be not a good candidate galaxy for measuring star rotation speeds. Perhaps edge-on would be better, so now we definitely have stars moving away from us and towards us, but notice that this galaxy has a rather dark dust lane down the middle, and that's making it difficult to see what those stars are doing. And so we wouldn't use a star which is strictly edge-on either. So we don't want face-on, we don't want edge-on, we want something in between, for instance like this. So here we have a galaxy in which we can see most of the stars in the galaxy, and some of them will be moving towards us and some away from us, and it's not edge-on, so the dust in this galaxy is not going to obscure our ability to take spectra. So if we think about whether the star spectra will be shifted towards the red or the blue, on the right that's not supposed to indicate the colour of the stars, it's just schematically telling us that stars on one side of the galaxy will tend to be blue shifted and stars on the other side of the galaxy will tend to be red shifted. Let's just ignore the green ones in the middle for the time being. So what would we expect? We can calculate the velocities of stars, but what would we expect that orbital velocity to look like? How should it vary as we look at stars further and further away from the centre of a galaxy? How would we expect the velocity of stars to change as we go from the centre of a galaxy to the edge of a galaxy? If a star was being kept in orbit around the galaxy because the object keeping it in orbit was all inside its orbit, as indeed it is in the solar system, then we have a very well-defined set of rules that say if a planet is at a given distance from the sun, you can see the x-axis here is talking about how far a planet is from the sun, and the vertical scale is telling us how fast that planet is going around the sun. You can see here that Mercury is going around the sun very quickly. Mercury is very close to the sun, it feels a very strong gravitational force, so it has to go round the sun quite quickly to stay in orbit. Whereas at the other end of the solar system, out here, Neptune at 30 astronomical units from the sun, it's a long way from the sun, it only feels a weak gravitational force, and so Neptune travels much more slowly as it goes round the sun. So that's a well-known relationship between orbital velocity and the distance from the star, assuming that everything that's producing the gravity that's holding the object in orbit is all concentrated in the middle. Of course, that isn't strictly the case for a galaxy because the stars that are producing the gravity are spread in a disk rather than all concentrated in the centre. That particular relationship, if we plotted it slightly differently, if we plotted it on log axes, we can see there's a very nice relationship between velocity and distance. But let's not worry about that. Let's just imagine that we have this curve and we have this rapid fall off of velocity once we are in a position that we are getting further and further and further away from the object that is keeping us in orbit. So we can make these measurements. Here we've got some observational measurements and I've superposed it on a little picture of the galaxy. So we're looking at the speed at which stars are moving as a function for how far away they are from the centre of this galaxy. So this is 10, 20, 30,000 light years from the centre. So stars that are rather close to the centre, remember all of the stars are not concentrated in a tiny part of the galaxy, they're distributed over the galaxy. So when we look at star speeds as a function of distance that is relatively close to the centre of the galaxy, we find that the speeds actually increase, unlike in the solar system. But the important observation is what happens when we get to stars that are outside most of the visible part of the galaxy. So this red ellipse there is, roughly speaking, an ellipse that seems to enclose something like 99% of the galaxy seems to be within that ellipse. We can't, of course, define a very sharp edge, but for the sake of argument, let's just imagine most of the galaxy is inside that red ellipse there. What would happen if we start measuring star speeds beyond 15,000 light years? You can see the dotted line there says, well, what we would expect if most of the mass of the galaxy is within the visible disk In other words, if most of the mass of the galaxy is coming from what the visible part of the disk, the visible stars and gas that we can see there, if that's where most of the mass is, then once we get beyond about 15,000 light years, we would expect the speed of the stars to come down. Just like we see in the outer part of the solar system, the speed is falling. For each planet further away from the sun, the speed is decreasing. So now we're moving away from the galaxy, we would expect the dotted line. So if the observation is the yellow dots, then do the yellow dots start coming down once we go beyond 15,000 light years? That is the crucial observation. Unfortunately, there aren't that many stars out there, so we're starting to lose the candidates that we would like to have, and it actually gets easier to measure the velocity of gas than it is the velocity of stars. But that doesn't actually matter, because what we're measuring is how much mass is keeping those objects in orbit. And it doesn't actually matter whether the object is an atom or a star. It's still the same gravitational pull from the center there. And what do we actually find? No, it doesn't fall as we go further and further out. If anything, it gets higher. In some galaxies it tends to flatten off, and the velocity of objects moving at greater and greater distances from the galaxy simply flattens out. In this particular case, it actually increases slightly. And what it definitely does not do is fall away. So you can see that the gas out here is moving so fast, we would expect that gas to be moving only at this speed here if it's being attracted to the galaxy that we can see. But it's moving a lot faster. It can only be kept in that orbit if there's a lot more mass in that galaxy than we can account for simply by looking at all of the stars in that galaxy. Here's the expression again. It's as if there is some additional mass, not accounted for by looking at all the stars. There's some additional mass that is not luminous, that's providing the extra gravity that's keeping the stars or the gas molecules or atoms orbiting at high velocities, even a long way outside what looks to be the visible edge of the galaxy. There's something else there. A second strand of evidence that there's something we don't understand. Dark matter seems to exist to account for what we see in star rotation. Correction, for stars moving in galaxy rotation. So what we actually see, what we would expect to see, a little schematic here, here's a little video of what we would expect to see if there was no dark matter in the galaxy and the mass of the galaxy was simply a result of the stars that we can see. We would expect the stars to be moving quite quickly close to the center of the galaxy, but notice the stars are moving quite slowly towards the edge. There's a little glitch in the video just because the video is a few seconds and then the video restarts. But if you just pin your eyes onto one of the stars towards the outer edge of the galaxy, you can see they're moving very slowly compared to the stars in the center, and hence we get that so-called rotation curve at just below the galaxy there. The velocity falls away as we go further away from the center of the galaxy. But that's not what we observe in practice. What we actually see is something akin to what's on the right. What we actually observe is velocities that don't decrease as you go further out from the center of the galaxy. They tend to flatten off. Sometimes they go up, sometimes they go down a little bit, but on average they seem to flatten off. And again, if you notice by following a star towards the edge, notice that the stars at the edge on the right are moving a lot faster than the edge stars on the little graphic on the left. So galaxies rotate differently if they have a substantial amount of dark matter. And what we see agrees with what's on the right, not with what's on the left. We seem to have a lot of explaining to do. Let's look at a third strand of evidence. Gravitational lensing. Now this third strand is quite unlike the previous two. We can calculate mass from its gravitational effect, not on galaxies in a cluster or stars in a galaxy as we've seen in the previous two strands, but we can look at the effect on light itself. Okay, dark matter does not interact with light. It doesn't emit light, it doesn't absorb light. Yes, that is true. But dark matter has mass. And if it has mass, it has gravity. We can see that gravity from the previous strands of evidence. And if the mass has gravity, gravity can bend light. So yes, dark matter will not absorb light or emit light, but it can bend light that already exists and is passing next to a massive object. So here's a little graphic that explains that. If we have light from a distant galaxy here that might look like that if we could see it clearly, this distant galaxy will be emitting light, and some of that light will come directly to Earth, but as it passes this big galaxy cluster, which is fortuitously sitting in between us and that more distant galaxy, this galaxy cluster has enough mass to bend the light. If you wish, you can think of it as the galaxy has enough mass to bend space or warp space, and the light is travelling in a curve because it's travelling through warped space. Doesn't really matter how you think about that. So just like light passing through a glass lens can be focused by the glass lens, so light from a distant galaxy can be bent by a galaxy cluster, a large mass, and that light might be focused towards Earth. It's not going to be a perfect lens like the lens in your camera or the lens in your telescope, your refracting telescope, so the galaxy gets quite distorted. If that's what the galaxy looked like in the first place, by the time the light has passed through a galaxy cluster, it may look rather distorted. But if we look at the distortion of light, and if we understand how mass changes space according to Einstein's general theory of relativity, then we can get an idea of how much mass there must be in that cluster in order to bend the light. Here's an example of one particular gravitational lensing phenomena. Here we have a slightly orangey galaxy sitting in front of, in line of sight, a more distant, rather bluish galaxy, and the bluish galaxy has been so distorted it's ended up looking like a horseshoe. It's probably a normal spiral galaxy. It's difficult to tell because the image of the galaxy has been so distorted it's almost formed a complete ring there. A good analogy of what's going on is to think about if we take a single source of light, for instance that candle, what if we were to produce a lens, not a good lens, but a rather distorting lens, for instance the base of a wine glass. If we hold the base of a wine glass up to the candle, as seen by the top right, we see that we don't see just a single image of the candle. It's now broken up into 3 or 4 images, each of which is distorted into a little bit of an arc. In the bottom right, we can see the candle has been distorted into what appears to be 2 arcs, one on each side of the centre of the stem. And if we position the wine glass very carefully, we can produce the image in the bottom left, where the candle is now imaged as a complete ring, as we saw almost in the previous image, where we saw a horseshoe where there was an almost complete ring. This particular phenomenon is called an Einstein ring if it just so happens that the lensing object is in just the right position to produce a ring for a more distant source. So we can see that a distant object might appear as 1 or 2 or 3 bright spots, and they can be distorted into arcs or possibly an entire circle. So when the lockdown is over, when you get the chance to have a romantic candlelight dinner with your loved one at a restaurant, make sure you pick up the wine glass and just check this out for yourself. So here's lensing in action. We have quite a large number of foreground galaxies that are looking a little bit yellowish in this particular image. And they have a very large mass, and they are distorting light from more distant objects. You can see some of these galaxies appear to be distorted into arcs. The more you look, the more you can see these long strands that appear very unusual, and these are probably perfectly ordinary galaxies in the distance being distorted by the light passing through this gravitational lens. The distorted images can tell us what the mass is. That's not an easy calculation to do. But given that if we use Einstein's theory of general relativity, we can say this mass in this position will distort space in this way and will make the light bend in this way. And it's a tricky calculation, but if we work backwards and say what must the mass have been in order to distort the images in the following way, looking at a Hubble Space Telescope image of the distortion produced by a cluster, the mass of a cluster, we can calculate how much mass must be there in order to produce this set of images. And what we find is that the mass that's producing those images is more than we can account for by looking at all the galaxies that we can see that are in that cluster, in that lens. So once again, it's as if there is some additional mass that is not luminous that's providing the extra gravity that is needed to bend the light and produce the distorted images. A third strand of evidence that there appears to be dark matter that needs to be in the mix if we want to explain everything that we see. There's a fourth strand of evidence which I'm not going to cover at the moment, but it'll be in the handbook in the handout if you want to have a look at that later. So, okay, I'm convinced there's enough evidence that something is missing from our ability to account for all the mass that's out there. The luminous mass doesn't appear to be the total mass. There's a lot of evidence that there's something dark out there, or something invisible out there. But what is it? Well, there are two main candidates for the composition of DM. From now on, I'm just going to abbreviate dark matter as DM. There are machos and there are WIMPs, rather odd names for possible candidates for the existence of dark matter. And I'll say a few words about each of those. Firstly, machos. A macho is a massive, astrophysical, compact halo object. Okay, massive, well, these objects have to be massive because we're trying to account for a great deal of mass. Remember, there appears to be more mass bound up in these objects than there are in all of the stars and all of the galaxies. So whatever these things are, they must be quite massive. They might be astrophysical objects. In other words, we're not necessarily looking for a fundamental particle. Maybe we're looking for some objects that are out there. Compact, well, in order that we've missed them, they must be quite small. What do we mean by a halo object? Well, if we think of a galaxy, possibly an elliptical, but it might make more sense to think about a spiral galaxy, there might be a well-defined nucleus, there might be a disk, there's bound to be some dust in there as well. But the halo is a large spherical cloud that surrounds essentially every galaxy. And quite often the halo extends out further than we can see in terms of simply looking at the visible part of the luminous part of the galaxy. So regardless of whether we're talking about a relatively flat spiral galaxy or a large elliptical blob, all galaxies will have a large, almost spherical halo around them. Is it possible that this halo is populated with a load of massive objects? Could it be bodies that are made of normal matter, and it just so happens that this normal matter doesn't emit any light, or perhaps doesn't emit much light, and hence we fail to see them up till now? Perhaps they could be black holes, or neutron stars, or white dwarfs. That sounds a bit wrong to talk about objects that emit no light, and then we say, could it be a white dwarf? Surely a white dwarf is white, isn't it? Well, yes, when they're made, a white dwarf is glowing white hot. But there are no more thermonuclear fusion reactions going on at its core, which means a white dwarf star will simply sit there and will cool down. So if we wait long enough, a white dwarf won't necessarily lose any mass, it'll still be a relatively massive object, but if we wait long enough, a white dwarf will simply fade away and will become too dark to see, and similarly for neutron stars. So, Is it possible that black holes or neutron stars or white dwarfs, things that we think we already understand, is it possible that there are lots of them out there and they would account for all of the dark matter? Well, if they are out there, how can we hope to see them? If we're agreeing that they emit essentially no light, then how can we possibly detect them? Well, we can come back to the idea that we touched on before, the idea of lensing. Not lensing from a huge cluster of galaxies, but lensing from individual stars. So what might happen is, if the universe, or at least our galaxy, is full of a lot of these objects, these relatively dark and relatively compact objects, let's imagine we've got a load of black holes. If there's lots of them out there, then perhaps if we stare at a distant star, it is possible that a black hole might happen to meander and end up on a fortuitous line of sight with that distant star. That's not going to happen very often unless there are lots of black holes around, in which case presumably this will happen quite often. If we stare at a star and measure its intensity, as the black hole happens to drift into our line of sight, then it can focus the light from that distant star, as we saw earlier with gravitational lensing of a galaxy cluster. Then the black hole passing in front of the star can make the star suddenly appear a little bit brighter, simply because of this focusing effect. And if the black hole then happens to drift away, the star goes back to its original brightness. So we don't expect this to happen very often, but if we look at enough stars and look at them all the time and keep watching them, then if there are lots of black holes out there drifting around, then every once in a while we would expect to see a star suddenly brighten and then get fainter again. And so that would be a characteristic sign that a very compact and dark object, if we don't actually see any object in our field of view, then something is actually causing that lensing effect. So that experiment was carried out some years ago. This is a picture of our Milky Way galaxy, of course seen from the inside, but if we imagine just for a moment that we've just stepped out of the Milky Way and we're looking at the Milky Way edge on, we see that at the centre of the galaxy here we've got a little bit of a bulge and we have the spiral arms coming out, but we also have satellite galaxies. Down here we have the small and the large Magellanic Clouds. So if we're sitting inside one of the arms of the Milky Way galaxy, if we were to look at the large or the small Magellanic Clouds, there's a certain amount of space between us and them. They are hundreds of thousands of light years away. And if there's lots of black holes around the Milky Way, in the halo of the Milky Way, surely there will be some of them in between us and the Magellanic Clouds. So if we stare at the Magellanic Clouds and stare at as many stars as possible within the Magellanic Clouds, and we make a note of what their brightnesses are, then if the halo of the Milky Way is full of black holes, every once in a while we would expect to see stars suddenly get brighter as a black hole happens to drift into our field of view. So that experiment was done. And the result was some of the stars showed this microlensing effect, but not nearly enough to account for dark matter. So yes, machos do exist. There are black holes out there floating around, but they can't account for more than, at best, a few % of the matter that we're looking for. The mass that we're looking for is rather higher, by a factor of 10 or a factor of 100, larger than can be accounted for by black holes or white dwarfs or other objects. Machos do not appear to be the answer. So what's the alternative explanation? WIMPs, weakly interacting massive particles. So not astrophysical objects, not stars that we sort of already know about and have simply found it difficult to detect. Now we're talking about something fundamentally different. This is a particle that we haven't found yet. We know about protons and neutrons and electrons and a whole zoo of other particles. But maybe there are some particles out there which are responsible for the dark matter. So they're called particles because there's something out there which is massive enough So they have to be massive particles. We can't have a whole load of lightweight particles because we would need a huge number of them. So let's assume that they are relatively massive particles. What do we mean by weakly interacting? Well, it means that they don't do much. Remember, you and I and most of what we see around us is made of particles that have, for instance, positive charge or negative charge, positive protons, negative electrons. We're made up of atoms. They're interacting with each other and interacting with light because light is an electromagnetic wave. Whatever these particles are, if these are responsible for dark matter, they can't be positively or negatively charged, and they can't be interacting with light, and probably not interacting very strongly with anything else at all. They have mass, so they have gravity, so they're gravitationally interacting with each other, but not through any of the other forces that we understand. So that's what we mean by weakly interacting massive particles. The catch is we haven't found any particles that meet the bill. The Large Hadron Collider has been smashing particles into each other for quite a few years in the hope of revealing what these weakly interacting massive particles might be. But so far, we have not found a convincing candidate. They interact through gravity, but not through electromagnetism. So in a sense, they're similar to neutrinos. Neutrinos are a particular type of particle, which we do understand. Some neutrinos come from the nuclear reactions in the heart of the sun, for instance. If these weakly interacting massive particles exist, we think they must be much heavier and travelling a little bit more slowly than neutrinos, which tend to go flying around at almost the speed of light. If WIMPs exist, they were presumably made in the Big Bang. That's the origin of everything, hence the Big Bang talk that I gave a couple of years ago, the beginning of everything. So we assume that WIMPs were made in the Big Bang if they do exist. And every particle appears to have an antiparticle. An electron has an anti-electron, a proton has an antiproton, etc. So presumably a dark matter particle has its antiparticle equivalent, an anti-DM particle. We don't see many of them. They are presumably now rather rare, but perhaps we can find them if we look in the best place to look. It's a bit like losing your keys. Where do you find your keys on a dark night? Well, you look under a lamppost. Not because they're likely to be under a lamppost, but just it's illuminated, so you're more likely to find them if they are there. So perhaps WIMPs, because they interact through gravity, maybe they're going to be attracted to the fact that there's a very large, massive object at the centre of our solar system. So maybe there's a few WIMPs in the sun, and maybe they are annihilating the dark matter and anti-dark matter particles. If they were to annihilate with each other, they might make neutrinos. So, given that we can't directly observe a dark matter particle, is it worth looking for neutrinos that we can't explain given our understanding of how the sun works? If we get a lot of neutrinos coming from the sun, perhaps some of them are coming from the elusive dark matter particle. So how might we find or detect these rather elusive neutrinos? Well, one way is to make yourself a very large tank of water. And that's what's happened in Japan, a so-called Super Kamiokande experiment, which is a large underground tank of water. Why might you do that? Well, again, let's draw an analogy. What happens when a fighter jet moves through the air faster than the speed of sound? The air can't get out of the way, and this object is moving through the air faster than sound can move through the air. The result is a shock wave. We often hear it as a sonic boom, if you think about Concorde days, for instance. And so just like this analogy with sound, there's an equivalent for light. If an object can move through a medium faster than light can move through that same medium, we get the equivalent of a sonic boom, an optical boom if you like. It's called Cherenkov radiation. Now we know that nothing can go faster than light in a vacuum, but if particles travel through, for instance, water, light doesn't travel at the same speed through water as it travels through a vacuum. Light gets slowed down by the water. So a fast-moving particle moving through water might be able to move faster than the speed of light through water. And that's what we're seeing here. This blue glow from a nuclear reactor has not been added as a Hollywood special effect. That's what happens when very highly energetic particles move through water faster than light can travel through water. You get a blue glow. And if we get a single particle travelling through a large tank of water, as it travels through the water, it can produce a blue flash. And that flash tends to be in the direction it's going, a sort of headlight effect, if you like. A particle coming down from the top left, moving through the water, would produce a flash of light which ends up travelling down towards the bottom right of the tank of water. So if you surround your tank of water with a whole load of light detectors, then if your light detectors go off down here but not over here, you've got an idea of which direction this particle came through your tank. And if you detect enough of these neutrinos over a period of months or years, as long as your experiment runs, then you can work out where did they come from. If at this time of day I get the light detectors down here recording a blue flash, then it means that the particle must have come from that direction. Does that correspond to where the sun was, or does it correspond to where the sun wasn't? We can start to build up an idea of where these particles are coming from. That is an ongoing experiment, as is an equivalent carried out at other parts of the world. You get an idea of just the size of these experiments when you see that if you take the water level down and look at the light detectors that are lining the inside of this cylinder, you realise just how big it is. And if you're having trouble seeing what it is at the centre of that image, that is two men inside a dinghy. So every once in a while the water level is taken down for people to do maintenance on those light detectors. So you can see it is a huge volume of water. But even that volume isn't necessarily as big as you would like, and there are other ways of taking these light detectors. You can see that they are, a little bit bigger than a football. You can take these light detectors, and rather than put them on the inside of a large water tank, an alternative has been carried out in the Antarctic, and that is the so-called ice cube experiment. The ice cube laboratory is sitting on top of the ice pack, but the detectors themselves are not sitting on top of the ice. The detectors, those sort of football-shaped light detectors, are set like a string of pearls into the ice pack itself. The ice is about 2.5 kilometres thick at the South Pole, and to give you an idea of scale, let's just put the Eiffel Tower down in the bottom right there. So what we're looking at here is if a particle comes and travels through the ice, it'll produce this same blue flash which can be picked up by these detectors, which are scattered over a volume which is roughly 1 kilometre thick, 1 kilometre wide, 1 kilometre deep. In other words, it's looking at particles that are travelling through a cube of ice 1 kilometre on a side, hence the name of the experiment, Ice Cube. The particle travelling faster than light doesn't really care whether the medium it's travelling through is liquid water or solid water. You still get effectively the same effect. So this is one way of generating a very large volume without worrying about how are we going to build a water tank that is 1 kilometre on each edge. Again, ongoing experiments trying to see if neutrinos are coming from the sun, and it's also looking for other particles as well. There is another possibility. As well as being concentrated perhaps in the sun, because the sun is a large source of gravity in the centre of our solar system, where else do we know that there's a large concentration of a massive object? Well, there might be a whole load of these WIMPs in the centre of the Milky Way for the same reason. That's a concentration of mass within our galaxy. And it's thought that if dark matter particles annihilate in the centre of our Milky Way, they might produce very energetic gamma rays. And hence there are experiments planned to search for these gamma rays. So again, this is the picture of our Milky Way. unwrapped, if you like, from an all-sky picture. And the centre of the galaxy is in this region here. We can just about see this part of the galaxy from England, but it's very low down in the south during the summer months. If you wanted to build yourself a detector which is looking for things coming from this direction, you wouldn't build it in England, you would build it in the southern hemisphere. And so there are plans to build a so-called Cherenkov telescope array. The Cherenkov light, remember, is the blue flash produced by an energetic particle. And a whole load of telescopes are going to be built. These telescopes aren't going to be trained only to look at the centre of the galaxy. These telescopes are looking up into the atmosphere, looking for the characteristic blue flash of particles within our atmosphere that are travelling through the air faster than light can travel through the air. You tend to think of light travelling through the air moving at, roughly speaking, the same as the speed of light in a vacuum. In fact, the air has a refractive index such that the light travelling through air is moving slightly slower than light travelling through a vacuum. And some of these very energetic particles, which can be produced by these very high energy gamma rays coming in, perhaps from the centre of the galaxy, these very high energy particles can be moving faster than light through the air. And they will produce a blue flash, and these telescopes will hopefully be able to detect these blue flashes in the sky. So if we think about it, now the whole of the Earth's atmosphere is being used as the detector. We're looking for particles coming in, not in a water tank, not in a cube of ice, but in many, many, many kilometres of the Earth's atmosphere. So we're increasing the volume that's able to detect these particles. So there are some big experiments that are being designed to detect dark matter, perhaps through their interactions in the sun, perhaps through interactions in the centre of the galaxy. But there are other laboratory-based experiments as well, quite a few in Europe and elsewhere in the world. So these are very much more compact experiments. I'm not going to talk about the detail of how these work. There are various acronyms describing various experiments that are being carried out. Here's just half a dozen, but there are perhaps 10 or 20 experiments around the world which are all trying to think of ways of how might we detect a dark matter particle if that dark matter particle happens to come into our laboratory and hit some of the atoms in our detector. So if you're interested, you can go and have a look at these various acronyms and go and see what these other experiments are doing. Many of these experiments have seen some interesting results, but many of the results are either contradictory or have not yet been confirmed. So they have seen things which could be dark matter particles, but they might be something else. So far, again, no confirmation of dark matter detection has been made. We must acknowledge that there is another possibility. Perhaps we have simply misunderstood how gravity works. Hence, we only seem to need dark matter because we're missing something about how matter interacts through gravity. Maybe gravity works differently on different scales. Newton says gravity is universal, but maybe gravity isn't universal. Maybe it works differently on the scale of the universe compared to the scale of the galaxy, compared to the scale of the solar system, compared to the scale of what's going on in Earth. If we take a couple of masses and try and measure how much those two masses are attracted to each other, maybe we would get a completely different result than if we worked with larger masses on a larger scale. So maybe we have to tweak the idea of how gravity works. There's a theory called modified Newtonian dynamics, MOND, which basically says let's tweak gravity in such a way that we no longer need dark matter. Well, yes, you can do that. You can change the way gravity works so that you do not need dark matter. That is true. However, in doing so, you generate a dozen other problems which you then have to deal with. So if you get rid of dark matter, you can only do so by generating a handful, a whole shed load of other problems which you then need to try and figure out how are we going to get rid of these other problems. So it's a possibility, but it has fallen out of favour because nobody has come up with a way of modifying gravity which A, gets rid of dark matter, and B, doesn't have any side effects. So does it matter, the final bit of the puzzle? It appears to be there. We don't know what it is, but who cares? What are the consequences of the existence of dark matter? Well, computer simulations tell us about how the universe started as a Big Bang and came to look the way it does now. We've got a pretty good idea of how the universe was born, the first 3 minutes, which generated all the hydrogen and helium in the universe, how we went from there to all of the structures we see, the galaxies, the stars, etc. However, if those computer simulations do not put dark matter into the mix, we don't end up with a universe that looks the way that our universe does. We don't end up with something that looks the same as what telescopes tell us is out there. In other words, the very early universe, in the first fraction of a second, when the observable universe was only the size of a golf ball or so, there were density variations corresponding to the dimples in the golf ball, if you want to think of them that way. And these dimples, these variations in density over time, when gravity had its effect, eventually formed the structures that we see today. In other words, if we take a relatively smooth bit of the universe, a cube that's maybe a few million light years on a side, if we let gravity do its work, then that matter will collapse into filaments and voids and will generate the cosmic web that we see on the largest scales in the universe. And where those little filaments connect with each other, that's where the galaxies and the clusters of galaxies form. But in 13.8 billion years, the age of the universe, we can only get a cosmic web which looks the same as the cosmic web that we see when we look out into the universe. We can only get that to work if we add a considerable amount of dark matter. We need an amount of dark matter which is significantly more than the amount of hydrogen and helium and everything else that we know was made in the Big Bang. So it would appear that we can only get the universe which we appear to live in if dark matter exists. If dark matter did not exist, the universe would not have had time to form galaxies and stars and planets and us. So on the largest scale, we see a foamy looking universe. We see a universe which is made with this cosmic web of filaments and voids. And the more we look in detail with our computer simulations, the more we see, yes, these filaments are feeding matter down into these little knots, which are where the clusters and individual galaxies are being made. And we can see that process at work within the confines of our computer simulations. So in terms of the consequences, yes, absolutely vital. So I've been talking about why it's dark, because its interaction between matter and light is different between dark matter and ordinary matter. I've given you 3 out of the 4 strands of evidence, and the 4th one is in the handout. I've said that dark matter is either machos or wimps. It doesn't appear to be machos, but we haven't found any wimps yet, so we don't know. And does it matter? Well, it matters for cosmic evolution. If dark matter didn't exist, we wouldn't have galaxies within the time frame of the age of the universe. We wouldn't have galaxies, stars, planets, and you wouldn't be listening to this talk. Thank you for your attention.